All right, this week we're going to start talking about making a forecast. So, if I want to make a forecast, what would I want to know? Uh, I think maybe it'd be interesting maybe to focus on the West Coast for a change. Not a lot going on across our area right now with the big high pressure sitting over top of us for the next several days. There is rain down to the south. However, along the frontal boundary here, there's out here to the west. What's happening out here? There's a front through now. Looks like low pressure's up in Canada somewhere, southwestern Canada. How is that going on? Interestingly, and puts out a map every day to try to give us an idea of what their general overall forecast is. So with that, let's take a look at that map. This should show that we have that low along the west coast there, front coming through. This is tomorrow's forecast, so it looks like there's going to be some precip moving into the west coast, particularly the northwestern coast of the United States, maybe even some snow in the higher elevations. If I wanted to know, for example, maybe how much amounts that snow might be, I would take a pick here. This is the quantitative precipitation forecast. Notice that the first day, not a whole lot of precipitation there. You'll notice that down in the southeast, where that low is going by and the overrunning, we have some decent precipitation there. And by tomorrow, day 2 precipitation, significantly more coming into the mountains of the northwest by day 2. So it looks like precipitation will begin to build up there. And all this is forecast. Forecasters at local offices, like the Seattle office, for example, would take this and then also look at other maps, guidance to try to figure out what might be the actual more detailed forecast. So, for example, a more detailed forecast for downtown Seattle, actually. And these are all the parameters that meteorologists, the public, to make your lives hopefully a little bit more informed, shall we say. The first graph here is temperature. We write, if you're a meteorologist at Weather Service, you put a forecast out for every 2.5 kilometers square. So it's basically a map of temperature. So here you have hourly temperatures. Notice, here is Sunday. Temperatures Sunday during the day go up into the mid to upper 50s, looks like. Dew point down here, a little bit further off. And they all kind of close in together by tomorrow night. Winds. Notice the winds. Southwest, southwest, turn to southeast here, and then back down to more southerly. Notice the precipitation here. Here is the probability of precipitation really spikes up between 3 and 4 p.m. on Sunday afternoon. So, if I'm writing this forecast in this detail here, what I just saw on that map is broad. What I showed you can be looked at over the whole country and is broad. But this is specifics. So if I lived in Seattle and I wanted an outside event tomorrow, well, I all of a sudden know that my probabilities of rain are going to be pretty relatively low in the 40% range in the morning into early afternoon. But boy, late afternoon and evening, that probability goes way up. So I better be prepared if I'm planning an event to think about that and know that, oh, maybe I may have to shift my time frame a little bit here. But let's look at a couple other things with this. Here goes west. I wanted you to see an atmospheric river, and there is a beautiful one out across the Pacific right here. You can see it. Look at it going from the tropical Pacific, and it's going to be into the northwestern part of the United States. So that is where the moisture is coming from. So now we know we have a broad area of moisture feeding into those things. Oh yeah, out there in the Seattle area and a part of Washington, mountains play a role. What I wanted you to notice here is notice on the lee side of the mountains, away from the wind, downslope, precipitation. So that would be an aspect. If I am a forecaster out in Seattle, I need to take into account. So that's part of it, just looking at what's going on right now. So now a couple different numerical models. Numerical models are the lifeblood of the Weather Service. This is a global forecast model. It's broader, covers the entire globe, and it runs out to 380 hours. So it's fairly long term. However, it also doesn't get all the fine detail, which maybe I might be interested in sometimes. You'll notice in 36 hours, tomorrow evening, Sunday evening, here comes low pressure forming right on the western part, just off the coast. Pretty strong jet coming down on that low and coming across down in here, probably revolving into that area during the evening hours tomorrow. So I'm going to be expecting some divergence developing across that area, which is going to feed into that precipitation. I get this forecast once every, literally it's hourly, and I can get the data for each hour. It only comes out 4 times a day, and that is another issue. Sometimes the models don't always get the perfect forecast because they don't always get the perfect information. Look out over the Pacific. There's not a lot of data there. Not a lot of data points to come up with an analysis of what is currently happening. We saw the satellite. We may have a few ships out there. But other than that, there is somewhat of a lack of data over the Pacific Ocean. Interestingly, we can look at some other parameters with this. Let's look at a higher resolution model. Now we're coming down to the NAM high res. This model allows convection. There's a difference. The GFS does not. Why is that important? Well, you may remember the hydrostatic equilibrium we talked about. And we talked about everything moving at a constant velocity. Well, in order to model that, GFS uses that kind of a model. Everything is moving at a constant velocity. Yes, that velocity can increase or decrease, but it's constant when it isn't accelerating. However, in a thunderstorm, think about it, very unstable air, you have a lot of acceleration of motion. So we have developed more detailed models now. We finally have the computer power to do it, that basically don't particularly use the hydrostatic equation perfectly. We add another term that accounts for all the acceleration due to strong thunderstorms. This model handles that. So this model is going to be slightly higher resolution because let's face it, thunderstorms are smaller resolution where the GFS may have a grid of 8 kilometers and can broad brush a thunderstorm. This will have a grid of 3 kilometers and can't. It needs to be able to understand what a thunderstorm is as far as the model goes. So you can see here, strong jet divergence over that area again. Notice that jet just moving across the northern part of the United States from west to east, pretty much zonal flow here. So that's what's keeping really good weather over Ohio for the first part of the week coming up. We can also look at another model, and this one is spaghetti. We call it the spaghetti model because it is a forecast based off of the GFS model, but what we do is we say, okay, this is what we have, we believe the observations are out over the Pacific and over the world. Now, let's tweak those observations a little bit, one way or another. We do that based on some statistical analysis. With that, We also rerun that same computer model with those slightly different observation conditions, initial conditions. We begin to generate, oh, that's not quite as exact as we thought we had. There's some changes in where the low is. For example, here, this is quite a little spread down off Seattle, up over north of Vancouver. That kind of a spread, as we've learned in extratropical, make a big difference in precip type and the amount of precipitation. But we also go even further with this. We take the current observations and we tweak our model. The model is an approximation. It's not perfect. So we tweak it. We make some approximations. We change them. Change the physics we're using to just slightly different. And what happens is, hopefully, in that spread of spaghetti that you're seeing there is the actual solution. If it is, we can see which ones have the most spaghetti, the most circles near them, and we can base our forecast on that. And if you go way out in the future here, I just wanted to give you an idea, looking in the future with this. Spaghetti. We'll just take this one again. And we're going to look way out, 168 hours. Let's do 144 hours. And you'll see all that spaghetti we were looking at before will get lots and lots worse. Try to figure out. There is a ton of possible solutions now. And our job is, and think about it, 144 hours out, a little bit over 5 days. The United States don't have too much problem. But if we're up in Canada and over the Pacific, lots of issues. One final thing is I wanted to be able to look at how we make temperature forecasts. Yes, I can tell you that I can think about it, the dry adiabatic lapse rate or the wet adiabatic lapse rate. If I know what the temperatures are aloft, I know approximately what the temperatures are going to be at the surface, the maximum temperature it can get to. And with that, dew points, wind, I can come up with an estimate for minimum temperatures. But we also have statistics. What they've done is for the last so many years, we've looked at how our models are doing, and we've used statistics to develop forecast of temperature. And this is a high temperature forecast based on those statistics with a whole bunch of different models put together to come up with. And you'll notice if I'm living in Seattle, well, I'm probably looking at highs 50 to 55, maybe 55 to 60 range. And if I'm off the coast, maybe a little bit warmer, 55 to 60. However, if I'm in the mountains, I'm back in, I'm in the 30s, in 20s even. So you can see how we can utilize this to provide detail, which is what you just saw with the earlier forecast. I wanted to just give you an idea, walking through the forecast process so you can apply everything you're learning into an actual forecast, maybe for your house. Who knows? If you have any questions, let me know.